Okay, thank you. I would like to thank the organizers for their support. This talk bases on my joint paper with my thesis advisor, Boban Velichkovic. My aim is to introduce a poset that is forcing with side condition, that is pure side condition without working parts, that is essentially due to Boban, and I will show that some combinatorial principles at omega 2 and omega 3 hold in the generic model that are well-known results, but we show that we have them simultaneously. I start with the background. In 2011, Christoph Weiss introduced some combinatorial principles that are TP, ITP, and ISP. In this talk, I only introduce ISP, and then Vienna and Weiss used this principle and proved that any standard forcing construction of a model of PFA needs at least a strongly compact cardinal. The origin of these principles dates back to works by Jech and Magidor. For example, ITP kappa holds for an inaccessible cardinal kappa, ITP kappa holds if and only if kappa is super compact. But this principle can be held for accessible cardinals like omega 2 or omega 3. One important byproduct of work by Vienna and Weiss is the guessing model, that I will give the definition of a guessing model that is due to Cox and Krueger. For this, I need a kappa approximation property introduced by Hampkins. For a cardinal kappa and models of a fragment of ZFC M and N, such that M is a subset of N, we say that the pair Mn has kappa approximation property if for any ordinal alpha in M and any subset of alpha that is in N, if it is the case that X is kappa approximated by M, means that X intersection Z is in M for all Z that has M cardinality less than kappa, then it should be the case that X is in M. And then we say that a model is kappa guessing model if intersection of M and kappa plus is an ordinal, and the pair M bar and V has the kappa approximation property where M bar is the transitive collapse of M. And now we can formulate ISP for a regular cardinal kappa. ISP kappa plus says for sufficiently big theta, the set of kappa guessing elementary substructures of H theta is stationary in H theta less than kappa plus, that is the subset of H theta of size less than kappa plus. It is not hard to see that ISP kappa plus implies the tree property at kappa plus. And this was the first central notion, and the second one is the approachability ideal introduced by Schellach in late 70s, and also extensively studied by him. For definition of the approachability ideal, I introduced the generators. For this, suppose lambda is a regular cardinal. A sequence of bounded subset of lambda is called a lambda approaching sequence, and we let BA for this sequence A be the set of all ordinals delta less than lambda, such that there is a cofinal set C in delta with order type less than delta, and we have this coherence property that for any gamma less than delta, C intersection gamma is on the sequence. And Schellach defines the approachability ideal at lambda to be the ideal generated by these sets and the non-stationary ideal at lambda. And Schellach asks if it is consistent to have a regular cardinal kappa such that the approachability ideal at kappa plus is the non-stationary ideal at kappa plus modulo the set of ordinals of cofinality kappa. The reason why Schellach asked this question is that the set of ordinals of cofinality less than kappa belongs to the approachability ideal, and if you have a cardinal lambda that is bigger than kappa plus, then there is a stationary subset of ordinals of cofinality kappa that doesn't belong to approachability ideal. And finally, Mitchell answered the question in 2009, assuming cardinal kappa, that is kappa plus mahlo, then he shows that the approachability ideal at omega 2 is the non-stationary ideal modulo the set of uncountable cofinality, the set of ordinals of uncountable cofinality. By theorem of Schellach, the large cardinal assumption is necessary, and it can be held for any regular cardinal kappa. That means approachability ideal at kappa plus plus is the non-stationary ideal at kappa plus plus modulo the set of ordinals of cofinality kappa. And now the question is that how we can connect these two notions. If you have an omega 2 approaching sequence, and M is an omega 1 guessing model of size omega 1, then the trace of M on omega 2 cannot be approached. That in particular says if ISP omega 2 holds, then S omega 2 omega 1 does not belong to the approachability ideal, but that's not enough to imply Mitchell's result. We need to say that no stationary subset of S omega 2 omega 1 belongs to the approachability ideal. For this, we introduced Fs kappa plus for regular cardinal kappa that says that there are sufficiently many kappa guessing models such that the trace of these models on kappa plus forms kappa closed an unbounded set in kappa plus. And this implies that the approachability ideal at kappa plus is the non-stationary ideal modulo S kappa plus kappa. And in order to show the consistency of this, we use two supercompact cardinals, and then we show that in the generic extension ISP omega 2, ISP omega 3, and Fs omega 2 hold simultaneously. The first, a smaller supercompact is, if you have a supercompact and an inaccessible above it, you can get ISP omega 2 and Fs omega 2, but for ISP omega 3, we need another supercompact. And for this, we use forcing bit side condition that introduced by Boban. For that, we have to use some sort of new models called virtual model that essentially introduced by Boban. And we don't use elementary substructures of H theta. We use elementary substructure of some and the extension of some elementary substructure of H theta. Boban invented this notion in order to iterate the semi-proper forcings with finite condition. So for this, we say that a set is admissible if it is transitive and is a model of ZFC. We can also add predicates, but here we don't need. And for an ordinal alpha in A, we let A alpha be the intersection of V alpha and A, that is the initial segment of A. And then here Boban defines the Hall is sort of S-column Hall, but for the definition we don't need to refer to the biggest structure. That is Hall of M and X for a submodel of A that is admissible is the evaluation of functions in M at finite sequences of X. And it has a key property that if M is an elementary substructure of an admissible structure, then the Hall itself is an elementary substructure, and moreover, it admits a minimality property that is the least elementary substructure containing M and X intersection A delta. That delta is the supremum of M in ordinal. Fix an admissible structure. We let EA be the ordinals that A alpha reflects A. In fact, in Boban's iteration style, the iteration machinery goes through this A, not all cardinals, all ordinals look up. And then we let for an ordinal alpha in EA, script A alpha be the size of A alpha that has the same size as A alpha. And finally, we say that a model M is an alpha model for alpha in EA if its Hall with A alpha is in script A alpha and is elementary extension of M. And we say that M is a virtual model if for some alpha in EA it is an alpha model. This alpha is necessarily unique and be denoted by eta M. And we say that M and N are alpha isomorphic. Here, of course, you don't need to say that M and N are virtual models. If there is an isomorphism between the halls such that the image of M under this isomorphism is N. It is an equivalence relation. And we need to introduce a version of epsilon. This is because in forcing side condition, forcing with side condition, usually you have a chain and you order the models, and but we can't use usual epsilon. This is it has a technical reason. We say that M is alpha in N if there is M star in N such that it's alpha isomorphic. And this isomorphism is continuous, meaning that if M is beta isomorphism to M star for unboundedly many beta below alpha, then it is alpha isomorphic. And we define the projection of a model, of an alpha model to some ordinal beta less than alpha. We take the Hall of M and V beta, then we apply Mostovsky collapse. So we get the image of M under this collapse. And we let M beta, the projection of M to beta, be this image. And it is a beta model. So here, there is an example, a concrete example that also is very important because our forcing relies on this. If you have an inaccessible cardinal lambda, then V lambda is an admissible structure. So we have E V lambda that we denote by E lambda. That is the set of alpha that V alpha is an elementary substructure of V lambda. This E, for any admissible structure A, EA is always closed, but maybe it is empty, but in this case it is a clubbing lambda. And this is a picture that if you have an element, M is a countable elementary, M is a countable submodel of V lambda, it's not necessarily an elementary substructure, but you take the Hall and then Hall is transitive and this elementary extension of V alpha, and M itself is also elementary submodel of Hall. And for alpha in E lambda, we let C alpha be the set of countable alpha models, and C less than or equal to alpha be the set of all countable virtual models that are beta models for some beta less than or equal to alpha. And script C is the set of all countable virtual models in V lambda. As we are going to use two types models for forcing with side conditions, we have to introduce another type that we call it Magidor model. We can use models of size Aleph1, for example, that are internally collapsed, but that is not enough for our purpose because we need some strong closure property. Magidor models, in fact, comes from Magidor's characterization of supercompactness that mentioned by Peter Hawley yesterday. In fact, we say that M is a Magidor model. If you take the transitive collapse, then the transitive collapse of M is V gamma bar for some gamma bar less than kappa. And V pi kappa is a subset of M, and we require cofinality of gamma bar be bigger than pi kappa. In fact, it says that if you have a Magidor's characterization says if you have a supercompact cardinal kappa for any gamma above kappa, there is gamma bar less than kappa, and you have elementary embedding from V gamma bar to V gamma. And these Magidor models are the image of V gamma bar under this elementary embedding, but we require also that cofinality of gamma bar be at least a critical point of elementary embedding. And for similar to countable case, for alpha in E lambda, we let U alpha be the set of all Magidor alpha models, and also script U be the union of all virtual Magidor models. Notice that we have sufficiently many of them. We have stationary many of them in V lambda. And we have to define something that is kind of a mystery. I don't know why we have to define it, but we have to define it. I don't know. We say that a model is active at some point in E lambda if you take the Hall of M and V kappa M, that kappa N and kappa, then this Hall intersect E lambda intersect delta is cofinal in E lambda intersect delta. And we have to define kind of virtual version of intersection, because in forcing with side conditions, you have two types model. You have to have some closure property about intersection. You have to connect these two collections. We define the meet only for different types. So if you have a Magidor model N and a countable model M, then we can take the transitive collapse of N that is in M. We assume that it is in M, and then we pull back the intersection of N bar and M. It is a countable elementary substructure of N, but it's not necessarily a virtual model, and we have to make it a virtual model. Then we project it to eta, that eta is this ordinal. Okay, let's see what it says. We take the maximum of ordinals which both N and M are active. This is because in virtual model you can have a model M and another model N that is epsilon alpha M, but N has the rank bigger than that of M. So N can be somewhere here and M here, and this pullback is the intersection here. And this model, for example, is an alpha model, is active. I mean, suppose that it is active at M, and then we want to put, because we want to use epsilon alpha chains, not usual epsilon chain. So we have to project N to alpha and then take the intersection. We would like if both of them are active at this point alpha, then we have the meet in this chain. So we would like to have n meet m here. So we project this set to make it a virtual model and also to be active at points that both m and n are active. In fact, if n meet m is active at some point, then both m and n are active. And if we have a bunch of models in script C, union script U, a bunch of Magidor models and countable models, and delta is an ordinal in E lambda, we set m restricted to lambda to be the projection of projections of models in M, script M, and we let m lambda to be those projections that are also active and delta. And the main forcing is this. We define inductively on E lambda. For an ordinal alpha in E lambda, we let m alpha be finite set of beta models for beta less than or equal to alpha that is closed under meets, and for every delta in E lambda that is less than alpha plus 1, m delta is an epsilon delta chain. And the ordering is that n script n is stronger than script m if any model in M is a projection of some model in N. Projection, I mean that N projected to eta M is M. And finally, we take the direct limit over E lambda, and the ordering is the same because of definition. And notice that M alpha is a complete suborder of M beta for alpha less than beta. Okay, if we force with this over a model that we have a kappa super compact and an inaccessible lambda above it, then we preserve omega 1 because m lambda is, I didn't define, a strongly proper, you can say proper, is a strongly proper for sufficiently many countable models. It preserves kappa because it is also strongly proper for Magidor models, and we have sufficiently many of them. And then it collapses cardinals between omega 1 and kappa to omega 1, and cardinals between lambda and kappa to kappa, that is omega 2, and makes continuum omega 3. In fact, 2 to the omega 2 is also omega 3. This is because we use lambda many countable virtual models. So, and the intersection of poset with a countable model is at the Cohen real. And so in this model, the generic by m lambda, ISP omega 2 holds and FS omega 2 holds also. And if lambda is super compact, then ISP omega 3 holds as well. And we can get more. In fact, we can make, by decorating the poset, we can make the set in the set I defined in FS omega 2, that is omega closed. We can make it a collab, a real collab, but we don't need to do that for our purpose. So that's it.